In a previous chapter, we learned about electrolytes. When electrolytes are put into water, they make ions. And we said that electrolytes were acids and salts, or ionic compounds. Well, acids and bases are electrolytes, and we're going to look at them in this chapter. Pay close attention if you're planning on going into a health field, as acid-base chemistry, understanding acids and bases and pH, are key to understanding a lot of the issues that go on within a body. Let's go to a definition for acids and bases. The first definition we're going to look at is something called the Arrhenius definition. Acids can be defined as those things that produce protons in water. Now, I just said proton, and you're looking at this equation here and wondering where the proton is. Well, let's just look at hydrogen. This is hydrochloric acid, and we put it in water, and it separates into ions. And you can see here there's a hydrogen ion, and there's a chloride ion. Because it's an electrolyte, it will separate into ions. Now, this thing right here is a hydrogen ion. Hydrogen is made of a proton and an electron. To make a hydrogen ion, you have to remove the proton to get the positive charge, remove the electron to get the positive charge, and what remains is a proton. So commonly, we call this a proton. So when I put something that is an acid into water, what does it do? It produces a proton plus a counter ion. And that's a definition of an acid, that it produces a proton. Bases are also electrolytes, and when you put them into water, what happens? They make a cation plus hydroxide. Notice this is an electrolyte because it's a metal with a nonmetal, so it's a salt basically. But this is the salt of hydroxide, so it makes hydroxide in water. So here are two simple definitions of acids and bases. We call them Arrhenius acids and bases, but it's limited, and we're going to look at another definition in just a little while. First of all, though, I want to talk to you about a proton. Protons do not exist in water. They react with water and form something called the hydronium ion. But if you showed every acid reacting with water to form the hydronium ion, yes, you would be more correct. But it makes a more complicated equation, and it's much simpler just to say it produces a proton and understand that a proton doesn't really exist in water. It's attached to a water molecule. Let's look at the equation for forming the hydronium ion. Here is a proton, and here is water. They combine, so 1, 2, 3 hydrogens, and oxygen, and a positive charge. So it makes complete sense. Anytime the word proton is used, you can substitute hydronium ion. Anytime you see the word hydronium ion, you can substitute the word proton. And when we start talking about pH, we're measuring the concentration of hydronium ions, but they call it pH for the proton. There's another definition of acids and bases, and that's the Bronsted-Lowry definition. In this, we're actually looking at the transfer of a proton. A Bronsted-Lowry acid is a proton donator, or it gives up a proton. So here's hydrochloric acid. We're going to look at it reacting with water. If you look at hydrochloric acid, beforehand the chloride has a hydrogen attached. Afterwards, it's chloride minus. It lost H+. It reacts with water. The water picks up the proton. So this water then forms a hydronium ion. What actually happened is the hydrochloric acid gave its proton up to the water. It is what's called a proton donor, so it's defined as an acid. The water took the proton. It's a proton acceptor, and so it's defined as a base. So whenever you see something that gives up a proton, it's an acid. Whenever you see something that takes a proton, it's a base. Hydrochloric acid and water here behave as an acid and base, but there's times that water can behave as an acid, and there's times that acids can behave as a base. And so this is a much more flexible definition, and it encompasses pretty much all of the acids and bases that we're going to talk about. Now, if we look at Bronsted-Lowry acids, almost all of the Bronsted-Lowry acids are also Arrhenius acids because they have a hydrogen atom in there and they give up a proton. So if you dissolve it in water, they'll make a hydronium ion or a proton. These are some acids. You notice that they all start with a hydrogen in the formula, except for this one. This is acetic acid. Organic acids have this functional group of a carbonyl and an oxygen attached to a hydrogen. We've seen this in fatty acids. So the organic acids, we recognize them as acids by this functional group. Bases that are Bronsted-Lowry bases have a non-bonding pair that grab a proton. So if I look at ammonia and it reacts with water, water gives up a proton to form hydroxide, and ammonia grabs the proton from water to form ammonium. We actually could define ammonia as a base because it produces hydroxide in water. So it is actually both an Arrhenius base and a Bronsted-Lowry base. Common Bronsted-Lowry bases have the non-bonding pairs, and hydroxide, because if you look at the Lewis dot structure for hydroxide, it has 1, 2, 3 non-bonding pairs on that oxygen. And so this is also a Bronsted-Lowry base because it has non-bonding pairs. So we recognize bases as metal hydroxide or as compounds that have non-bonding pairs that can grab protons. Proton transfer is an acid-base reaction. Notice we're showing how an acid and a base work here. Here is the acid. It gives up the proton to form this anion. The base grabs the proton to form this cation. It's proton transfer. So it's basically loss of a proton and gain of a proton. When this acid loses its proton, this pair of electrons that forms this bond actually stays on the whatever atom that is, as a non-bonding pair right there to give us its negative charge. This non-bonding pair reaches out and grabs a proton, and that non-bonding pair actually forms this bond. Now, if you look at this, there's an equilibrium arrow here. And in an equilibrium, you have a forward reaction and a reverse reaction. Look what happens to this acid. It forms this anion. But this anion can grab this proton and go back to this acid. When it does that, it's accepting a proton, and so it's a base. As a result, we call it the conjugate base of this acid. This base grabs a proton and forms this species right here. But this right here, Hb+, can lose its proton and go back to the base. As a result, we call this the conjugate acid of this base. So here in this reaction, hydrobromic acid reacts with water to form bromide and a hydronium ion. This is the acid and this is the base. This is the conjugate acid of hydrobromic acid, conjugate base of hydrobromic acid, and this is the conjugate acid of water. In order to form a conjugate base, all you have to do is remove the proton. In order to form the conjugate acid, all you have to do is add a proton. So now go ahead and try to form the conjugate base of carbonic acid. The conjugate base of carbonic acid is formed by removing a proton, so there will only be one hydrogen, and because the proton has a positive charge, it leaves behind a negative charge on the remaining molecule, and this is bicarbonate. So carbonic acid and bicarbonate are conjugate acid conjugate base pairs. What is the conjugate acid of ammonia? Well, ammonia will gain a proton to act as a base. So we take this formula right here and we put a proton onto it and we get ammonium. What is the conjugate base of hydroxide? Well, we take hydroxide to hydroxide, we add a proton, 2 hydrogens and an oxygen. The negative charge is then canceled by the positive charge of a proton, and we get water. I write water this way, but we can also write water this way.